Hi folks, this is the second video in the Simple Harmonic Motion series. In this one, I give you an introduction to differential equations. I'm not going to teach you how to solve differential equations. You don't need that for this course, but you do need to recognize differential equations and get a feel for their solutions. Now, one of the greatest mathematical physicists of the last century was a guy called Freeman Dyson. Now, when Dyson was 14 years old, his parents took him off for a summer vacation. And what they would do in England in those days is go, rent a beachside cottage or something, and they'd go and stay there for a couple of months. Now, Dyson took with him this book on differential equations by Piaggio. Now, this is not an easy book, but it goes from introduction all the way to very difficult problems in differential equations, including numerical solutions and all kinds of other advanced techniques. Now, remember, he was 14 years old. Now he goes there to the beachside cottage and sits out there with his notebook and pen and works something like 14 hours a day, and over the 2-month vacation completely masters differential equations. Now that probably laid the foundation for a fantastic career as a great mathematical physicist, and he was also one of the co-discoverers of quantum electrodynamics. Now the point I'm trying to make here is differential equations is a very beautiful topic in mathematics. It's a lot of fun. But then I'm just going to give you a flavor of differential equations. So let us start with a very simple idea. Imagine that we have in a petri dish a lot of bacteria, and there is sufficient amount of nutrients that the nutrients are not going to run out as the bacteria divide. Now, as the bacteria divide, the number of bacteria grows, so the number of bacteria is a function of time. Let's write that down. So we start with writing down the number of bacteria as a function of time. Each bacterium doubles in a certain amount of time. So the number of new bacteria that are formed per unit time is proportional to the number that are already there. In other words, the rate at which the number is changing, dn by dt, is proportional to the number of bacteria that are present at that instant. So let's say lambda is the proportionality constant and n is the number of bacteria at time t. This is a differential equation because it contains a derivative. Any equation that contains a derivative is a differential equation. Now we are used to algebraic equations. For example, we are used to equations like 2x minus 7 is equal to 5, and that will give us x equal to 6. Now the solution for this linear algebraic equation is a number. Supposing we have a quadratic equation, for example, x squared minus x minus 6 is equal to 0, then it has two solutions, x equal to 3 and x equal to minus 2. Now in this case, we find that there are two solutions, both are numbers. But when it comes to differential equations, the solution of a differential equation is a function. So what this differential equation is asking is find a function n of t which satisfies the equation. In other words, find a function n of t which, when we differentiate with respect to t, gives us back the same function except it's multiplied by a positive constant. Now we know that an exponential function e power x, when it is differentiated, gives us e power x, gives us the same function back. So let us try n is equal to some constant e to the power of lambda t. Right now this is just a guess, and like I said, I am not going to be teaching you systematic methods for solving differential equations. We're just going to get familiar with them. So if this is our guess, let us verify and see if this is a solution. So let us differentiate. So dn by dt, a remains where it is, derivative of e to the power of lambda t with respect to t, first differentiate with respect to lambda t, and then by the chain rule, if I differentiate lambda t with respect to t, I get lambda. But this is nothing but lambda times a e to the power of lambda t, which is n. So dn by dt is equal to lambda n. Therefore, this is a perfectly good solution. It's a perfectly good solution for any value of a. For example, 28 e to the power of lambda t will satisfy the equation, or 6 into 10 power 23 e to the power of lambda t will satisfy that equation. So A can be anything. So A is an undetermined constant. So this is called the general solution for the differential equation. When we put in a value for A, for example 28 or 6 into 10 power 23, we get a particular solution for the differential equation. Now we find the particular solution by using an auxiliary condition. For example, we might say that at time t equal to 0, the number of bacteria is N0. So if we add this condition to this equation, let's see, N at time t equal to 0 will be A e to the power of 0, which is A, and that's equal to N naught. So now we can write down the equation N is equal to N naught e to the power of lambda t, which is the solution of this differential equation for this particular initial condition. And this is called a particular solution. Let's try another example. Supposing we have a radioactive sample, a large number of radioactive nuclei. Let's say the number of nuclei we have is N, and as they decay, the number changes, so N becomes a function of time. The difference is, in the case of bacteria, the number of bacteria was increasing, whereas here, the number of radioactive nuclei is diminishing. Now, each radioactive nucleus decays with a certain probability per unit time. And so the number of radioactive nuclei that decay per unit time is proportional to the number that's already there. So you might be tempted to write again, dN by dt is proportional to the number of nuclei. But wait a minute. dN by dt is the rate of change of the number of nuclei, whereas the rate of decay is minus dN by dt. I'll explain that quickly. If you have 100 rupees in the bank and if it becomes 95 rupees, the decrease in the money is 5 rupees. The change in the money is minus 5. So decrease is minus of change. So the rate of decrease is minus of rate of change. So our differential equation becomes dN by dt is equal to minus lambda times n. So let's try a solution. Let's guess that this might be a e to the power of minus lambda t. And one of the things we need to learn in this course is to be able to verify whether something is a valid solution. So how do we verify this? We plug it into this differential equation. So let us differentiate. dN by dt will be a, derivative with respect to minus lambda t is minus lambda t. By chain rule, since I want the derivative with respect to t, I get minus lambda. Again, notice that this is nothing but n. So we get dN by dt is equal to minus lambda n. So it satisfies our differential equation. This is a solution, and this is our general solution because it's valid for any value of a. Once again, supposing we are told that the number of nuclei, undecayed nuclei at time t equal to 0 is N0, what do? We plug in the initial condition. So n at time t equal to 0 is a e to the power of minus 0, which is again 1. So this is a is equal to N0, and so we get the particular solution for this initial condition as n as a function of time is N0 e to the power of minus lambda t. So this is an exponential decay. In the case of bacteria, we got an exponential increase. In the case of radioactive nuclei, we get an exponential decrease. Now, let's think of a simpler differential equation. Now, the simplest differential equation that I can think of is this. Let's say y is a function of x, and let's write down dy by dx is some constant, let's say 5. Now, what is this differential equation telling us? It's telling us find the function y of x, whose derivative is 5. We can guess that easily, but let me put it in a different way. If I plot y as a function of x, the slope dy by dx is constant and equal to 5, which means all straight lines with slope 5 will satisfy this differential equation. What's the equation of a straight line? Y is equal to mx plus c. M here is 5, so 5x plus c. Once again, we have an undetermined constant For different values of this constant, we get different straight lines. Take a look. All these lines have the slope 5, but each one of them has a different y-intercept, so C is different. We are plotting y versus x. So a straight line passing through the origin would be y is equal to 5x. Now you see, all these solutions form a family. And this family has something in common. They all have the same slope equal to 5. Now if I add an auxiliary condition, for example, if I say y at x equal to 2 is equal to 3, then we can use this to find the value of C. Let's do that. Put x equal to 2, so I get y is 3 equal to, put 2 here, that becomes 10, x is 2 plus C, and straight away we get C is equal to -7. And so the differential equation has this general solution. If I add this auxiliary condition, we get the particular solution y of x is equal to 5x minus 7. What do you suppose the differential equation is, which is obeyed by all straight lines, no matter what the slope? That is, lines which are described by y is equal to mx plus c, where m may be any finite number and c is also any finite number. That is, we are including all straight lines except vertical ones. The property of a straight line is its slope is constant. That means the rate of change of the slope, that is d by dx, rate of change with respect to x of dy by dx, which is nothing but the second derivative d2y by dx squared, that should be equal to 0. So this is the differential equation, which is a second order differential equation whose solutions are the equations of straight lines. So this is the general solution. A particular solution might be y is equal to 2x minus 7. Now you get the particular solution from the general solution by putting in an auxiliary condition. Here the auxiliary condition may be that the slope is so much and the y-intercept is so much, or the auxiliary condition might be that it has to pass through two given points, and that will determine uniquely the straight line, and that is called a particular solution. Before I get to simple harmonic motion, let's look at something much simpler. An object moving in one dimension with a constant acceleration. So if I look at the velocity of the object as a function of time, we can write down this equation. The rate of change of the velocity with respect to time, which is the acceleration, is a constant, and let's put the constant equal to a. Let's assume that a is a known number. Maybe it's 5 meters per second squared, or 9.8 meters per second squared, or 1 meter per second squared, or whatever. Now this is a differential equation. A is a constant. Now the solution for this equation, remember this is exactly like dy by dx is equal to 5. And the solution for that was y is equal to mx plus c, m being 5. So the solution for this is going to be similar. Same equations have same solutions. V is equal to at plus c. Y is equal to mx plus c. Now to find c, we use the condition that the velocity at time t equal to 0, let's call it a known number u. Let's put t equal to 0 in this equation. So v is equal to, at time t equal to 0 is c, and that is u. Therefore, this equation can be rewritten as v is equal to u plus at. Now you can verify u and a are constants. If I differentiate this, I will get dv by dt is equal to a. We have a spring of constant k and block of mass m, and while it oscillates, the net force on the block in the x direction is minus kx is equal to mass into acceleration, d2x by dt squared. Now this is a second order differential equation, and the solution for this equation, x as a function of time, is some undetermined constant a sine omega t plus phi, where a, omega and phi are constants. If I differentiate this twice, you can do this yourself, d2x by dt squared will turn out to be minus omega squared times a sine omega t plus phi. But then this is nothing but x. So I get d2x by dt squared is minus omega squared x. If I compare it with the differential equation, we get omega squared should be chosen as k by m, or omega is square root of k by m. So the moment you're given the spring and the mass, I know omega. A and phi, on the other hand, are determined by initial conditions. Let's do that quickly for one example. Let's imagine that I pull it by 10 centimeters and release it from rest. So we have x at time t equal to 0 is 0.1 meters, and I release it from rest, so dx by dt at time t equal to 0 is 0. So let's plug it in. X at time t equal to 0, if I put in t equal to 0, I get a sine phi. So the first equation gives me a sine phi is 0.1, and the second equation I get from differentiating this. Dx by dt is equal to omega a cosine omega t plus phi. Put t equal to 0 again, I get omega a cos phi. That's the other equation. Omega a cos phi is equal to 0. So from the second equation, I can choose phi to be equal to pi by 2. 90 degrees, cos 90 is 0. If I take that and plug it into the first equation, I get a is equal to 0.1. So I get the particular solution, which I am going to write down. X is equal to 0.1 sine omega t plus pi by 2. So goodbye for now until the next video.